Hello! In this video, we're going to prove the following theorem. Suppose phi is a group homomorphism from a group G to a group G bar, and suppose A is an element of G. Then for all integers n, phi of A to the power of n is equal to phi of A to the power of n. Now, a group homomorphism is a function from one group to another that preserves the group operation. In other words, we have, for all elements x and y in G, phi of x times y is equal to phi of x times phi of y, where x times y is the operation happening in G, and phi of x times phi of y is the operation happening in G bar. Now, let's talk about what this equality is saying. Now, in the case where n is a positive integer, this equality is telling us the following. It's telling us that phi of A times A, and so on, multiplied by itself n times, is equal to phi of A times phi of A times phi of A, and so on, multiplied by itself n times. Now, in the case where n is equal to 0, this equality is telling us phi of A to the power of 0 is equal to phi of A to the power of 0. Now, any element of a group to the power of 0 is equal to the identity element. So let's say that the identity element of G is E, and the identity element of G bar is E bar. Well, then in that case, this equality is telling us that phi of E is equal to E bar. And a property of group homomorphisms that we have proven is that a group homomorphism carries the identity element of one group to the identity element of the other group. And because of this, well, that tells us that the n equals 0 case is immediately true. So then, what is this equality telling us in the case where n is a negative integer? It's telling us the following. If n is a negative integer, then this equality is saying that phi of the inverse of A times the inverse of A times the inverse of A, and so on, negative n times, is equal to the inverse of phi of A times the inverse of phi of A times the inverse of phi of A, and so on, negative n times. Okay, now in previous videos, we have given a more careful description of how exponentiation of elements in a group works. And that description was as follows. Given G is a group element, then G to the power of 0 is equal to the identity element of the group. G to the power of n plus 1 is equal to G to the power of n times G for all integers n greater than or equal to 0. Now, these first two lines are recursively describing what happens when we raise G to the power of a positive integer. It's really just going to be G multiplied by itself that positive integer number of times. So then what happens when we raise G to the power of a negative integer? Well, if n is a negative integer, then G to the power of n is equal to the inverse of G multiplied by itself negative n times. Now, a property regarding exponentiation of elements in a group that we have proven is the following. G to the power of m times G to the power of n is equal to G to the power of m plus n for all integers m and n. Okay, so now let's get into proving this theorem. Now first, let's say that the identity element of G is E and the identity element of G bar is E bar. Now we're trying to prove for all integers n, this equality is true. And we're first going to prove for all integers n greater than or equal to 0, this equality is true. And we're going to prove that using induction. So let's start with the base case. In the base case, we're trying to show that this equality is true in the case where n is equal to 0. So we want to show that phi of a to the power of 0 is equal to phi of a to the power of 0. So let's start out by writing the left-hand side. Now, any element of g to the power of 0 is the identity element of g. So this must be phi of e. And we know that group homomorphisms carry the identity element of one group to the identity element of the other group. So phi of e must be equal to e bar. But any element of g bar to the power of 0 is equal to e bar. So in particular, phi of a to the power of 0 must be equal to e bar. So this shows that phi of a to the power of 0 is equal to phi of a to the power of 0. So this completes the base case. Now let's move on to the induction step. In the induction step, we give ourselves an arbitrary integer n greater than or equal to 0. And we assume that this equality is true for that arbitrary integer n greater than or equal to 0. From here, the whole goal is to show that this equality is also true for n plus 1. So we want to show that phi of a to the power of n plus 1 is equal to phi of a to the power of n plus 1. So let's start out by writing the left-hand side. Now, according to the recursive part of our definition, a to the power of n plus 1 is just a to the power of n times a. But then, by definition of a group homomorphism, we can split this up into phi of a to the power of n times phi of a. But then, by the induction hypothesis, we know that phi of a to the power of n is equal to phi of a to the power of n. Then, we can apply the recursive part of our definition again. This is just phi of a raised to the power of n plus 1. So, through this chain of equalities, we have shown phi of a to the power of n plus 1 is equal to phi of a to the power of n plus 1. So, this completes the induction step. And so, this closes the induction. We have proven by induction, for all integers n greater than or equal to 0, this equality is true. So we've proven that this equality is true for all integers n greater than or equal to 0. Now we're going to prove that this equality is true for all integers n less than 0. Because once we do that, that'll prove that this equality is true for every integer. So to prove that this equality is true for all integers less than 0, well, let's give ourselves an arbitrary integer less than 0. Call it n. Well then, the negative of n is an integer greater than 0. Now the whole goal with this arbitrary negative integer n is to show that this equality is true. And to show this, the idea is as follows. We consider doing phi of a to the power of n times phi of a to the power of negative n. Well, according to this property, we can just add the exponents. This is just going to be phi of a to the power of n plus negative n, or just phi of a to the power of 0. But then, any element of g bar to the power of 0 is equal to the identity element of g bar. So this is just equal to e bar. But remember, phi of e is equal to e bar. And we know e is equal to a to the power of 0. And according to this property, a to the power of 0 can be expressed as a to the power of n times a to the power of negative n. And then, applying the definition of a group homomorphism, we can split this up into phi of a to the power of n times phi of a to the power of negative n. And now, let's use the fact that we've just proven by induction. This equality is true for all integers greater than or equal to 0. So in particular, it must be true for the positive integer negative n that we have here. So substituting n for negative n, we have that phi of a to the power of negative n is equal to phi of a to the power of negative n. So we can re-express this guy as this. So this chain of equalities tells us that this guy is equal to this guy. And notice, both guys contain phi of a to the power of negative n. So applying the cancellation law, we can cancel out the phi of a to the power of negative n's. We're left with phi of a to the power of n is equal to phi of a to the power of n. And so this shows, given an arbitrary negative integer n, this equality is true. So we have for all negative integers n, this equality is true. So we have proven that this equality is true for all integers greater than or equal to 0, and now we have just proven that this equality is true for all integers less than 0. Therefore, it must be true for all integers. And so this completes the proof. And so yeah, that's pretty much it for this video.